Okay, so I want you guys to go ahead and mark this. This is 10.3. This is what we call the complex plane, which is the imaginaries. If you guys kind of remember, you have your imaginary unit I. And then this is called de Moivre's theorem. So a lot of French mathematicians, so de Moivre. And if somebody's had French, you probably say it better than I do. But that's going to be his particular theorem that we're going to look at as well from this section. So I'll give you a minute to get it labeled. Let me get the definition started for you. So this is, we're used to the coordinate plane. So right now we've got rectangular coordinates, correct, which we normally think of as x, y. This is going to get confusing because sometimes I'll tell you write it in rectangular form, and they actually mean a plus bi. So just hang in there. I'll have you write it down. But so right now we do have rectangular, x, y. And then we have polar, r theta, that we can use. So we know how to convert between the two. Now you're dealing with your imaginary numbers where you have the complex plane. And just so you guys know, kind of on a bigger level, all your real numbers are in the complex plane, and then the complex plane has all the imaginaries too. So all the i's are in there, so your non-reals. The imaginaries are graphed on the y-axis. So they make all the real numbers along x, and all the imaginaries are on y. Do you guys kind of see it? And so the way they label, these are called your complex numbers, and I'm going to explain this a little bit more, is right here. So notice this is the imaginary, this is the real, and this is your complex number z. And so what they like to do when they write it in this form, I actually like to write y, I, but I'll try to remember the book likes the I back. This is called the real part, and this is called the imaginary part. Why is that one called the imaginary part? Because it's attached to what? The I. Do you guys see it? Now, just so you know, what happens if y is 0? What would happen to z? You'd have x plus what? 0 times I. And so what do you get? Just x. So that's why I was saying the complex plane actually contains all the reals. Because if you don't have the y, all the real numbers are represented as x. Makes sense? But if y is not 0, then you get all the i's. Does that make sense? Like your 3 plus I or 7 plus I. So you kind of have this big, this is the complex plane. They usually kind of put a dash, and then your reals are kind of in there. Make sense? And so all these are the i's, if you will. Do you guys have it? Yeah.
Are we going to convert the i's?
Yeah. Yeah, we're going to convert. We'll actually be able to go from a plus bi or x plus yi to polar. We can go to polar form, and we can go back even to rectangular. So I'll show you. So yeah, we can go convert back and forth. All right, do you guys kind of understand? So the real part and the imaginary part. Okay, all your reals are in there, and these are all your a plus bi's where the I stands. It's not going to go away, so it won't be where b0 or y0. Okay, so let me move down a little bit. And they have it plotted there in the corner. You can see there's your, how do you plot that? You go out a distance x and up a distance what? Y, because the y is the imaginary part. So just like you would plot rectangular xy basically. And then do you guys see that blue part? Does everybody see the blue, which we always think of as the radius, right? How do they get that? They use Pythagorean theorem by saying x squared plus what? Y squared. Do you guys see it? And that just has a name. It's called the magnitude or the modulus of your complex number z. So I will go ahead and label that there, but I like, of course, the picture the best. So the magnitude or the modulus, and really, you guys, that's truly just what we always think of as what? R. The only difference is this is mandating that R be positive. Remember when we had polar in the past, remember R could be positive or what? Negative. But here it's making the square root positive. Do you guys see it? Because it's talking about a distance. So magnitude or modulus of z. All right, I'll give you a minute for that. Okay, if I move the page over, if your complex number is x plus yi. What would the conjugate be? Well, what do you do to always get the conjugate? You change the middle sign, correct? The only difference is they note it with a z bar. So when you see z bar, they mean the conjugate, which means the middle sign has changed. Are you guys okay with that? So it's always like you've kind of thought about conjugate. It's just that you're dealing with a complex number. And remember, your complex numbers could be reals or it could be truly imaginaries. So if the y is 0, you just have a real number. And if y is not 0, then you've got an imaginary number. So just keep in mind your complex. That's just the way they notate it. I don't know why. Don't ask me. I don't know sometimes why math people have decided to do things a certain way. I'm sure there's some reason for it, but so that's your reals and your imaginaries. It's the complex numbers. I keep wanting to say a plus bi, but let's do the x and y that they're using. Okay, now of course, we want to be able to convert back and forth because we never want to be restricted to where we have to stay in one notation. We want to have the freedom to go back to what we want to use. And so you can easily transfer over into writing these as a polar number. So let me move down a little bit and I'll show you. So this is writing them in polar form. And it's really, really easy because you guys already know x is what? R cosine theta, right? What's y? Yeah, so x is our cosine theta, y is our sine theta, and then all they did is factor out the r. Do you see it, the common r? And so when you want to write your numbers in polar form, you just put the r out front and you say cosine theta plus I sine. There is some restrictions, and you guys, I get tired of writing the cosine theta plus I sine. So I want you to know sometimes I will write it like this. That's a common notation, RCIS. We do that a lot. And that way you don't have to write, you only have to write the one angle. I'll show you. Okay, the one catch is if you're in polar form, remember they want you to keep the R what? Positive, that's the first thing. And the other thing is they want you to stay within your standard angle. They want you to move counterclockwise and stay within your first 4 quadrants. If you're not in there, you've got to adjust it. You've got to move it into where it is and satisfying that restriction. I'll put CIS theta, or CIS theta. So you will see that. You'll be like, what's the CIS? It means R cosine theta plus I sine theta. So you'll just see it written that way a lot because you'll get tired of having to write it all the time. Okay. All right, I'll give you a minute to get that. Okay, so I'm going to look at the first example with you all. So here's the instructions. And it says, plot each complex number. In the complex plane and write it in polar form. And the book is asking for degrees. I'm actually going to do both degrees and radians because I really like the radians. So I'll show you both, and then you can do either way on the homework. So we'll do both degrees and radians. Because I'll probably start with radians knowing me and then convert it over to degrees. All right, and so the first one we're looking at is number 17. We have negative 3i. And so we want to plot that real quickly. So remember, this is the imaginary. So that's the I. And then let me mark in right here for the x-axis, that's your real part. Okay, so notice here, we know a complex number is normally written as z equals what? X plus y I, correct? So what's your x in this case? It's got to be 0. Do you guys see it? So really, this is the same thing as 0 plus what? Negative 3i. Do you guys see it? So your real part, which is the x-axis, is what? 0. And your imaginary part is what? The negative 3. Makes sense? So what would you do? You do 1, 2, 3, and that would be your negative 3i. Are you guys okay with that? Right, because the x was 0. It's just like plotting x and y. It's just that the imaginary part goes, the I part goes on the y-axis. Make sense? Okay, now they want us to convert this over and write this as polar. So let's write polar form real quickly for a complex number. So you know, to get it in polar, we want r cosine theta plus I sine theta. And I'll show you the other notation here once we get it written. All right, it's actually really easy to get r, but remember, r is really the square root of what? X squared plus y squared. And you guys already know that. It's just making it positive. That's the only difference. And so in this case, what did you say x was? And what's your y? It's always the coefficient of the I, right? Which is what? Negative 3. Does everybody see it? So to get r, you would do the square root of 0 squared plus negative 3 squared. So that's the square root of 9, which is what? 3. You actually could have gotten that from the picture. Okay. Now what about theta? Remember, for polar, they want you to keep the r positive. That was the first thing, correct? And where did they want theta? Between 0 and what? 2 pi. So you've got to keep that in mind, that they want you to stay kind of where you're used to. So what's something that we could use that's located where 3i is as far as theta goes? 3 pi over 2. And you'd have to use the 3 pi over 2. You can't use negative pi over 2 because of the restriction that they put polar form in. Makes sense? But that's okay. That's at least what you would normally do. So you would say, oh, okay, theta is 3 pi over 2. Make sense? So I always plot them first, just like I did before, even though we're dealing with complex numbers. You know, remember with rectangular, we always like to plot first and then kind of convert. You want to do the same thing here, because sometimes you can just get it from the picture. All right, so the way you technically write it is you would say it's 3 times, you would say cosine of what? 3 pi over 2 plus I sine of 3 pi over 2. I'll show you a few ways to write this. Now, if they wanted, that's radians, right? If they wanted degrees, what's 3 pi over 2? 270, right? So you could write cosine of what? 270 plus I sine of what? 270. Does that make sense? Just don't forget your degree symbol. So one's written in radians, which is what I prefer, and the other is written in degrees. Make sense? Or, because math people don't like to write, right? They just always are trying ways to abbreviate everything. You could write it like this. Okay, so or, that's the other way you'll see it. Make sense? And you'll get tired of it pretty soon. You'll be like, what was that shortcut notation I can use again, right? All right, so let's kind of make a little step here. If you want to go from complex form to polar form, plot it, find your r using the formula, and find your theta either from the picture or using tangent. I'll write that out real quickly. Are you guys okay with that? All right, so let's write this. So to go from complex, and sometimes I need to show you that in the book. And they use, it doesn't matter where you put it, but they put it on the back, so I'll do that. To polar, first plot the point. Second, find R. Easy enough, right? And then third, find theta from picture. And you can use the fact that tangent theta is equal to what? Y over x. Sometimes you'll get an undefined. Like in that last case where x was 0, you can't get it from that formula, right? You had to look at it from the picture. But, you know, you would see that anyway. Sometimes not, though, and then you can use it. Okay. Okay, I want to show you one more converting over to polar form. We'll do, again, both degrees and radians just to make sure. And then I'll give you a couple more theorems to write down. So, everybody okay with that? You got it? Okay, I'm going to come back and grab the instructions. Everybody's got that down, right? All right, so I'm going to move it over. All right, let's look at one more. And so for this one, we're going to look at question 23. We have -2 plus 3i is your complex number. And so the first thing you want to see, let's go ahead and get this plotted. -2 means this way, correct? And then +3 means what? Up. So remember, this is x and this is the imaginary. So you're going to go 1, 2, 3 up. And so this is your point, -2 plus 3i. You guys okay with that? Everybody got it? All right, so to go to polar, we're going to get r. We know x is -2. What's y, guys? It's just 3. Does everybody see it? You don't put the y in. Remember, it's just the coefficient. So then to get r, you're going to do the square root of x squared plus y squared. So you're going to have -2 squared plus 3 squared. So that's what, 4 plus 9. You guys getting square root of 13? Okay. All right, now I can't get theta in this case from just looking at the picture, but I do know theta needs to be located where? In quadrant 2, and I'm getting that from the picture, so I know that. And now I need the reference angle. And to get the reference angle, you're going to use the fact that tangent is, again, what? Y over x. And so tangent theta, what was y? We said it was 3, and what was x? -2. You can do, and you actually are in this case, you're going to have to use your inverse here. Now, we'll do both degrees and radians, but when you guys know tangent, right, you know your main points. We know 45 would be 1, right? We know 30, 60, it's either square root of 3 over 1 or root 3 over 3 or 1 over root 3, right? It's none of those, nor is it the quadrantal. So in this case, if it's not known to you, you have to approximate it. You won't have any choice. So we'll do it in both degrees and radians. So you're right. How do you get it? You're going to do theta. You're going to take the inverse tangent, correct, of 3/2. Now, why am I keeping it positive? What would the negative do? It wouldn't give me the reference angle. Are you guys following me? So remember, to get the reference angle, just plug in the positive. If you forget, it's not a big deal. It'll give you a negative and just take the negative out. It's not huge. All right, so let's go to, I'm going to go to my calculator real quickly. I have it here somewhere. And right now I'm going to make sure, I'm going to do radians first, and then I'll show you guys real quickly. Actually, we'll do it side by side. We'll do radians and degrees right next to each other. So let me see. I'm in radians right now. So I'm going to do inverse tangent of 3/2. And you guys double check me. That's giving me about 0.98. Anybody else get that? Okay. Then let's do it in degrees. So this is radians. I'm just going to real quickly switch my mode over to degrees. I'm going to hit enter. And then, that didn't do it. I was hoping it would just do it automatically, but it won't. Okay, so 3/2. Did you guys get 56.31 degrees? Okay.
So which one should I use?
You know, it's really up to you. The book was specifying, and I'm not really sure why, degrees. It wanted degrees. But sometimes I really like to work with radians. So I'm going to do it both ways, and then you guys can just kind of pick. Because on the test, I don't care. You can do degrees or you can do radians, whatever you're comfortable with. So however you happen to see it is fine. Are you guys all right with that? You matched me on that? There's a problem here, though. I can't really say that's theta yet. Let's call that the ref. What's the problem? Why can't I call it theta? It needs to be in quadrant what? 2, and it's not. 56.31 degrees is in quadrant 1 because it's the reference angle, right? Are you guys okay with that? Or it's less than 1.57 for you following me? Okay. So how do we actually get theta? To get theta into quadrant 2, do you guys remember how we do it? Pi minus, right? Pi minus ref. Because you want to put, let me show you visually. You want that 56, what was it, 0.31 degrees here. So that's your theta right there. So you would do pi minus ref. Make sense? So do pi minus the 0.98, or theta equals what? 180 minus the 56.31. You still following me? Okay. So on this one, I'm getting pi minus 0.98. Did you guys get 2.16 for radians? And then for degrees, let's see. How about 123.69? Okay. Y'all just double check me on that. Make sure that's okay. Everybody got it? Okay. There's no point to go to new screen, right? I'm going to make this fit. Okay. So our R would be, or Z, they usually call it Z. I'm sorry, we don't use R. It's in the formula. So our complex number Z would be R, which was square root of 13, CIS of what? 2.16, that's in radians. You guys okay? Or Z would be square root of 13, CIS what? 123 point what? 69 degrees. You following me okay there? Yeah. But if it had been known to you guys, like if it had been from your 30, 60, 45, just use your exact numbers. That's what it's going to want. They'll come out a little bit more nicely for you. But if it's not, then you can't do it that way. You just have to approximate. It's not a big deal. It's very similar. You just approximate it. Okay, the last thing I think I can do is, let me show you a couple things in the book. So I want you guys to write down this wording just so it doesn't throw you off. I'm going to go to page 745, and right here kind of in the middle, let me see. Couple of things. The first thing is I don't want you to be surprised when you start hearing this part. They call theta the argument of your complex number Z. So when you're like, what are they talking about the argument? They mean the theta. So like whatever we found, I can't remember what we just got, but whatever that theta wound up being, they call the argument of the complex number. So that's the first thing. All right, then a little bit above, is don't be thrown off when you've got a complex number. That's standard form. Now just to mess with your head, It is in rectangular or Cartesian form because x, y are the rectangular coordinates of the corresponding point, which makes sense, but it's kind of a little, sometimes it messes with students' heads. It's like, why are they calling that rectangular form even though it's a complex number? Because you easily can see what x and y are. Does that make sense? If you wanted to go back to rectangular, all you would have to do is see what x is and see what y is. That's it. And then you'd have your rectangular point. Okay, so I give you a minute just to get that part down. Yeah, it's sad. It's so sad. Okay. All right, let me show you one conversion and then I'll get the videos. I will have to, okay, so this says write each complex number in rectangular form. All right, and we're going to take a look. Let's do 28, and then I'll stop after this today. So we've got 2 times, we have the cosine of 5 pi over 6. You guys were like this is easy, times the sine of 5 pi over 6. And all they want us to do is go back to that a plus bi form. I know it says rectangular, but remember, your rectangular form means you're writing it in x plus y. I keep saying a, but just bear with me, x plus yi form. It's because they use a plus bi so much, but that's okay. All right, so this is easy for us. You basically solve your sine and cosine. So we feel like we're in the beginning of the course. So you've got to look at 5 pi 6. So for 5 pi 6, first of all, you guys, what's the reference angle? So either know your points on the unit circle or draw your triangle. It doesn't matter which one. You probably don't even need to draw it at this point, but I'll just do it anyway. All right, then you need to know where it is. So I'm going to take 5 and divide it by 6. And I'm getting about 0.83 pi. What quadrant, you guys? Yeah. 2. Less than 1, but greater than 0.5 pi. Make sense? Okay. So we'll call this z. We'll be fancy, and we'll call our complex number z. Now, notice what I like to do, and this is because math is just always so much fun. Z looks like 2. Z's not going to go away. You will have z in Calc 3, so just try to get used to it. With z, what I do is put a line through it, and then with my 2, I make the bubble. That way my 2 and z don't get confused. All right, I'm just trying to help you out. So I don't care how you do it, but some way in your notation, make sure you know 1 is z, and you know 1 is 2, because you're going to be seeing z again. So, okay, now let's look at it. Cosine 30-degree reference angle, we're right here, in quadrant 2. First of all, cosine in quadrant 2 is going to be what? Negative, am I right? Now, with a 30-degree reference angle, we know cosine is what? The adjacent over what? Hypotenuse. What do you guys see? Square root of 3 over 2. Or if you know your points, it's fine, right? So square root of 3 over 2. Done. Everybody all right with that? Now, don't forget the I stays. And now you're going to look at sine in quadrant 2. Sine in quadrant 2, positive or negative? Positive, so I was right to put the positive sign there. All right, and then with the 30-degree reference angle, how do we get sine? 1/2. Does everybody see it okay? You guys good there? Now you're going to distribute your 2. So what's going to happen to the 2's then? Do you guys see they cancel? And so what's z? Negative root 3 plus what? I. Or you could put, I wouldn't put 1i. Math Lab's it's going to throw Math Lab off, even though it's the same thing. So don't put the 1 in there. So you just say, oh, okay, so rectangular form would be negative square root of 3 plus I. Make sense? And the reason, remember, they call it rectangular is because it's so easy to get to rectangular. Rectangular, the x-coordinate would be negative square root of 3. The y-coordinate would be 1. Are you guys all right with that? Okay. And that's it. Pretty easy, right? Okay. All right, I'm going to turn this off.